Go. All right, so I am going to give a brief talk about some very broad stuff about functional programming, not about anything in particular, but just kind of functional programming in general. So I'm going to just kind of jump right in and start off with some code because I want to make sure that this is as concrete as I can possibly make it. So I'm going to start out with a Fizzbuzz implementation. So are you familiar with Fizzbuzz? Okay. Yeah. So Fizzbuzz is like obviously a really, really simple program. It's a little contrived, but this is an example of a pretty standard imperative implementation of Fizzbuzz. So we just kind of loop from 1 to 100 with an imperative for loop, and then we just kind of say, all right, well, is it divisible by 15? If it is, print out Fizzbuzz. If it's divisible by 5, print out buzz. 3, print out fizz. Otherwise, print out the number. And this is a really totally standard, reasonable implementation of Fizzbuzz. I don't really think there's anything wrong with it. But it is worth noting that it is a very imperative implementation of it. So what does that look like? Well, for one thing, we mutate I every time we go through the loop, right? So we're mutating variables. And we also kind of have this mixture of our logic and our I/O, right? So we have all these console logs interspersed with our program logic. And that's fine. I think for this really simple program, that's probably a totally fine thing to have, but it's not particularly functional. So the reason I actually decided to give this talk in the first place was I came across a sort of functional implementation of Fizzbuzz that actually was not originally in JavaScript. Obviously, this is in JavaScript, and I ported their code to JavaScript. But this was just somebody in kind of an IRC channel that I was in. They said, hey, I'm trying to get into more functional programming. I made this Fizzbuzz implementation, and it looks kind of like this. And so they said, is this a good implementation of Fizzbuzz functionally? So, right off the bat, there's a couple things that make this more functional than the last implementation. One, we're recursing instead of using a for loop, right? So we've got this loop. We have this Fizzbuzz function that we're defining, and we recur to increment the number each time instead of mutating a variable. And we kind of also have our logic and our I/O is kind of separated out. And also we're using lazy stream. So this is a little tiny lazy stream library I implemented just to port the code over. So this is definitely a lot more functional. There's not any of that imperative mutation, but I actually hate this program. I really dislike this program. I think it's really difficult to read compared to the first one. It's difficult to understand what's going on, and it's a lot bigger. There's more stuff going on in it. And so I was really interested by that because this is something I've seen before. A lot of the stuff going on in this program looks functional. We got lazy streams, we got recursion, but I don't think it really takes advantage of any of the things that make functional programming really good. And it means that if you're writing code like this and calling it functional, then maybe you're kind of you'd be led to believe, well, functional programming is not that great. This is clearly worse than the program I had before. So I wrote another version of the program, which is the way I would write it, and it looks like this. So this is another functional implementation of Fizzbuzz, and there's a couple different things about it that are interesting, but the most important one by far, I think, that I really want to draw your attention to is that there's no recursion. This program is totally functional, but there's no recursion whatsoever. In fact, there's not a loop, there's not recursion, there's a map, and we're using kind of this higher order function. But this is kind of I think a easier to reason about version of this program. We've got kind of this Fizzbuzz function that just operates on one number, and it returns Fizzbuzz, buzz, or fizz, or the number converted to a string. And then we just map that function over an infinite lazy stream of natural numbers starting from 1. And that's what that stream.naturals1 function does. So before I continue, before I get into exactly the details of this, because this is a little bit of a contrived program, but I think it demonstrates some of the things that are interesting about kind of the differences between imperative programming and functional programming. I want to make it really clear that these three programs are written in JavaScript, but there's nothing that's special about JavaScript to any of the things I'm talking about. This is a totally language agnostic talk. And to demonstrate that, I ported all three of these programs to 3 other programming languages. And I think it's you don't have to look at the details of every single one, but it's interesting to kind of see the shapes of the programs in each language. So the first one I did was I ported it to Clojure, because Clojure is another functional dynamically typed. Yeah, that's a blank slide. So I ported it to Clojure, and I said, all right, so here's the first one. Clojure is another dynamically typed functional programming language. And so this might be a little hard to see, but if you can't see like exactly the details of it, it's not a big deal. Just like take a look at the size and the shape of the program. So this one, it's also imperative. It uses doSeq, which is kind of just a standard iteration construct, and we just print out as we loop. So again, we're interleaving those effects and our logic. This is the second one that uses lazy streams and uses recursion. And again, you can see it's a lot bigger. And then we've got the final one, which just uses kind of a separate function. And it's a little bit bigger than some of the other ones because I had to re-implement the naturals function at the top. But for the most part, it's not that much bigger than the imperative one. But that's Clojure. And Clojure is also very similar to JavaScript. Obviously, it's very different from JavaScript in a lot of different ways. But it's a dynamically typed functional programming language. And you know, you might not say JavaScript's a functional programming language, but it has a lot of functional programming features. But it's dynamically typed. They're both dynamically typed. So I said, well, you know, could you do it in another programming language that's statically typed? And you totally can, obviously. So I did it in Haskell. I really like Haskell. But Haskell's statically typed. So one of the other interesting things about Haskell is that Haskell's a pure functional programming language, but you can totally write that imperative solution in Haskell without too much difficulty. So this is like that imperative solution, and it's imperative. It interleaves effects and logic. It loops from 1 to 100. Then also here's the sort of recursive one, and here's the one that uses a separate function. And these ones I think are all a little more similar in size because Haskell is a pretty concise programming language, but you can still see like there's difference in size and shape to each of these programs. But that's not really interesting because Haskell is a functional programming language, right? Of course, the functional programming language is going to be good at doing functional programming. So what about Java, right? Like Java, if you could do it in Java, you could probably do it in any language, right? Like Java is a language that people consider it's really object-oriented, it's really imperative, but you can totally do all these things in Java as well. So here's, you know, your standard kind of Java implementation of Fizzbuzz that's imperative. These ones are a little bigger because Java's a little more verbose, but here's the recursive solution with just a little tiny lazy sequence library that I implemented. It's just like 100 lines of code. And then finally, here's the functional separate one that I really like. And again, it's not that much bigger than the imperative one. And this uses Java 8 lambdas, Java 8 streams. But for the most part, I think it's actually really nice and readable. So, you know, you can totally do functional programming in any programming language. And to really emphasize that, I want to compare two of these programs. The one on the top is the first one in Haskell, and the one on the bottom is the last one in Java. And Haskell is a pure functional programming language. Java is an imperative, object-oriented programming language. The program on the top in Haskell, I think, is way less functional than the program on the bottom. So just because you're using functional programming concepts or a functional programming language does not mean that you're doing functional programming. So with that out of the way, I want to, again, actually like focus on these JavaScript programs and say, all right, why is it? Because it's great that I can say like this program is really functional and this program is not very functional. But that's not terribly meaningful unless you define what the difference is. So again, this program uses a bunch of kind of functional programming buzzwords. It uses recursion, it uses immutable data, it uses lazy streams. It looks like a functional program, but I'm saying it really kind of isn't. So what I'm going to kind of propose is that these three things that people often talk about in functional programming, they're not the essence of functional programming. They are nice building blocks, but you can do all three of these things in any programming language, in any programming style. What's really interesting about functional programming is kind of the way you structure your programs, not just kind of the way that you, the individual pieces that you build them out of. So if you look at this third program again, there's a couple of aspects to it that I really like. So one of those things is this notion of whole meal programming. I'm going to assume that you're not familiar with the term whole meal programming. So the notion of whole meal programming is this idea that you build big programs out of small pieces, and you sort of talk about whole data structures at a time, operating on a whole stream or a whole big data structure in a single expression, rather than saying like, oh, well, I'll loop over the data structure and I'll operate on each kind of atom of it at a time. So what I mean by that is if you look at kind of the middle block of this program where you've got that stream.map call, that's mapping a function over an infinite stream of numbers. And that's really interesting, and obviously we can do that because it's lazy, right? So we don't have to realize the whole infinite stream into memory. But that's really interesting because it means that in a single line we're talking about the whole data structure. And being able to do that is really powerful because it means you can think at a really high level. And that's kind of aided by this notion of function composition and sort of higher order functions. So we can pass the Fizzbuzz function into our stream.map function. We can take two functions, we can put them together. But also, and this is something that I think isn't talked about very much, but I think is actually really important in functional programming, is the separation of logic and data. And this is not something that I hear people talk about very often, but if you think about this, like, there's kind of two parts to this program. There's the function that defines what it means, what the Fizzbuzz logic is, right? It says, like, given a number that's divisible by 3, you produce Fizz. But that's totally separate from the part of the program that builds up a data structure. It's a separate function. They kind of are put together right at the end. And by doing that sort of thing, you get some interesting separations of concerns properties that I'm going to talk about in a little bit. So it might seem like I'm trending towards kind of a definition of functional programming. But I'm not. I'm not going to define functional programming. Functional programming has been around since the 60s. There's a million different kind of implementations and interpretations of what functional programming means. But basically, I think there's a lot of different ways to do functional programming. But what I can come up with are kind of some basic general principles of if you're going to do functional programming. And if you're interested in doing functional programming, then these are some things you can follow. And I'm not even really going to claim that they're better or worse than other paradigms of programming. But if you are interested in doing functional programming and these things make sense to you, these are some 3 really simple principles that you can follow that are applicable to, I think, any programming language. So before I get into that, any questions so far?
So at the beginning you say no recursion. So what's so wrong about recursion?
It's a good question. So I think one of the things that people often say, like, loops are bad, right? Because loops, you take a variable and you just increment it, and basically that means there's a lot of issues with loops. One of the things about loops is that it makes you very indexed obsessed, right? You always think about indexes into things rather than just like going through elements in a data structure. But ultimately that's not like a huge deal, and you've got for each loops and stuff like that. The nice thing about recursion is that it kind of breaks you away from some of that stuff, but you're still thinking about, like, recursion and loops are almost exactly the same. They're two different ways of structuring the same thing. So if you are using recursion, that might be a little better, but it's almost like, you really want to think at a higher level and think about these. One of the nice things is that, like, folds and maps and filters, those are sort of patterns of recursion that come up over and over and over again. And it's way more expressive to talk about that than it is to talk about the, like, let's process each individual atom of data at a time. So, recursion is sometimes useful, but for the most part, the vast majority of the time, you don't need to drop down to that low a level. You can operate at a higher level and at a higher abstraction. Does that make sense?
Yeah.
Okay, cool. Anything else?
No,
all right, great. It's a good question. All right, so 3 principles of functional programming. My first one's going to sound really silly. It's going to sound really obvious. But my first principle is literally just write functions. And it's going to sound really dumb. Like, obviously, if you're going to do functional programming, you need to write functions. But I specifically say functions. And I mean not methods, not classes, not procedures. What do I mean by this? Well, like, a method is a function that's kind of attached to an object, right? In an object in the object-oriented sense. And it has this, like, bundle of data that it carries around with it. The problem with methods is that you can't really, like, put them together very easily with other methods because, again, they're, like, attached to this thing. They're not values that you can pass around. So methods, and I'll get to that in a little bit about why that's doesn't quite fit my definition of what you want. Similarly, like, classes, those can emulate functions, but they've got all this other stuff associated with them. So, if you've got a language where it doesn't have first-class functions, you can use a class to emulate a function, and that's fine. But really, you don't want to be carrying around this extra stuff. And that's related to the fact that you don't want to write procedures. A procedure is a sequence of instructions that you execute from top to bottom. A function is a mathematical function, right? You pass a value in, you get a value out. That's all that happens. And that's really important because my second point is you want to write functions that compose. And so if you have these really nice pure functions that don't do anything but what they say they do, and they only talk about their inputs and their outputs, then you can take two functions and put them together end to end, and you can know what they're going to do together. You can get this really nice reuse. And again, like, that makes it hard to do if they've got this bundle of state that you're carrying around with them. But if they're just these little atomic bits that you can put together in interesting ways, then a lot of the time you get this really interesting reuse out of them. So, this is like higher order functions, function combinators. This is something that, like, I don't think people talk about all that much either, especially in the object-oriented world, because you don't really think about it that much. But, like, your abstractions that you write should compose. And if your abstractions, like, if you write two abstractions, and they're great abstractions, and you love them, and you say, this is great, I don't have to do, one thing at a time. I can think at a higher level. That's great, but if you can only use one of the abstractions at a time, if you can't put them together and use them both at once, then you're kind of tying yourself up in knots. You're kind of backing yourself into a corner. So really try and make it so that if you build some abstractions, can you use them together? Well, if not, why not? And also make it so that your abstractions are domain specific. This is also something that I think people who are interested in functional programming often overlook. They're like, I use a functional programming library. I use Lodash or Ramda or Scala Z or any of those functional programming libraries. And that's great. That's like a great starting point. But they provide a bunch of functions that are totally unrelated to your domain. They're just like standard functions that are useful everywhere. But you as a programmer, you're going to have to come up with your own abstractions that are related to the problem that you're solving, and you can build those out of those smaller kind of independent pieces. But you want to make sure that those abstractions that you create are also functional, and they also compose, and they also fit together, and they're these nice pure functions. And so don't feel like I had this little like functional DSL that I drop into to do like data transformation, but then the rest of my program is imperative. If you do that, like, that can work. It's not necessarily a bad thing, but you'll get a lot more of the benefits out of functional programming if you apply it throughout your program. And so this kind of brings me to my third and final point, which is really simple, and it's mostly small. So write functions that compose mostly small. Prefer lots of little functions. Build programs out of small pieces. This is something that I also think is, like, people talk about this a lot. They say, try and build programs out of small functions. But oftentimes it's not clear to people what that means. They think like, I've got a big function, it's 20 lines long, I'll chop it in half into two functions, one that's 10 lines long, one that's 10 lines long, and then I'll write another function that calls them both. And that's obviously not useful. That's not like that just moves your code around, but it just makes it harder to follow. It doesn't make it easier to understand or easier to use. But what I really mean by this is kind of try and figure out how to take apart different responsibilities of a function. And I really mean like rethink the notion of single responsibility. Usually when we have the notion of single responsibility in our code, we think about it in terms of like some domain responsibility. So we have something that handles users. We have something that handles, rendering a view. And that's great. Those are like good things to keep separated. But there's also kind of this notion of what if you could separate your domain logic from just kind of like standard little function combinators that happen to be useful to what you're writing, but they're separate from your business logic entirely. And I think this is something where functional programming gets a lot of reuse and it really excels at, but sometimes it's difficult for people to visualize. So I want to give a couple of examples of where all these things like actually apply, because it's really great for me to say you should follow all these steps, but if I don't demonstrate what that looks like in practice, it's probably not super meaningful. So before I do that, any questions on these three things? Cool. So the first example I'm going to give two examples. The first one is Redux. So obviously you're familiar with Redux. But if you're not familiar with Redux, then it doesn't really matter that much for what I'm going to talk about. It's a state management tool for front-end JavaScript applications. But the basics are that you've got this notion of kind of your application state, and you keep your state totally separate from your rendering functions. And you've got these components that take pieces of your state and they render it into views. I'm not even going to talk about like that view layer stuff. I'm really just going to focus on the data. And so what you often have is you have stuff like this, where you've got some state, and obviously a real application has lots and lots of state, but this is just a simple piece of state that has like a user and some user data, and it also has like some auth token. And so you might have some component that needs the user's name, but needs it all concatenated together into a single string. And then it might also need the auth token. So you could write this map state to props function, which basically maps a piece of your state onto like the properties that your component consumes. And you might say, well, all right, well, I'll take all the pieces of the username and I'll concatenate them together using the ES6 string interpolation syntax. And that's fine, like that's great. So now your component is just really simple. It just takes a thing and renders it. And that's nice, doesn't have any logic there. The trouble, of course, is that like you might end up copying and pasting this string because you write this like once per component. You might end up copying and pasting this like string interpolation all over your code base, and that would be terrible. So obviously, we all know how to solve that problem, right? Like what do you do if you have duplication of that kind? You write a function. It's not complicated. So we can do that, and we can write some functions that just like grab the pieces of our state and map them to whatever we actually need in our components, and then we can use those functions everywhere. But as your application grows, you might have like a lot of different things floating around in your state, and you might have a component that needs lots of different pieces of your state. And it's nice that you have these individual functions because they kind of decouple the details of like how to get that thing out of the state from the actual shape of your state, which is nice because that means that if you change the shape of your state, you don't have to update all your U-layer stuff. But the downside to this is that you have a lot of duplication, right? You've got this like username, user email, user email. Not really concise, and this might seem a little bit silly, but again, it's a really simple example because it turns out that you can't really have complex examples on slides. But the point is, like, and this is a real example, by the way. This is a real application that we have here at CJ. This is an abstraction that we came up with. So how could we reduce the duplication? If you're not thinking super functionally, this seems like, well, you can't, right? Like there's nothing to remove here. There's no duplicate. This is just like boilerplate. But you can actually reduce the duplication a little bit. And so we wrote this function called object view. And what I want to make very clear here is that this object view function knows nothing about Redux. It knows nothing about our application. It's a really, really tiny 2-line function. But the way it works is it takes this, it's a curried function, so it takes an argument, it returns another function that takes an argument. And so what it does is you give it this argument called prop mappings, and then it produces a function that maps state to props. And the way it works is each prop mapping, the prop mappings argument is an object, a JavaScript object that maps names to functions that are functions on the state, right? So each key is a name and each value is a function. And then we just use map from Ramda, which on objects just maps over all the values. And we just apply the view function to the state object that we get passed in to produce a bunch of props. And again, this is like a really simple example, but the point is this is a really simple function combinator, and you could come up with it. It's not like super fancy, but it's useful, and it demonstrates how like you can kind of tease apart things that are related to your domain and things that are just generally useful utilities. So that's a really simple example. I want to give a more complex example that I think is maybe a little bit of a better motivator, but we'll take a look. However, it's not in JavaScript anymore. It's in Haskell. But I'm going to assume most of the people who like are interested in functional programming but are not functional programmers probably don't know Haskell because Haskellers tend to be very functional already. So for that reason, I'm not going to focus on almost any of this. I'm actually going to focus on just like a really small piece of this function that we wrote. And this is a real function that we wrote in a recent application, a recent piece of code. But basically, we wrote this function called assertunique. And the idea is that we take this set and we produce a map as a result of it. So like this set, this is kind of the k comma v syntax is like a tuple. So it says given a tuple of, and this is a type, so given a set of tuples from keys to values, then we want to produce a map from keys to values. Now those two things are like really similar, right? Like a list of key to value mappings and a map from key to values. Those are almost exactly the same. There is a difference though. Can you think about like what the difference between those two data structures is besides just performance characteristics? There's actually like a meaningful difference. There's something that the set can have that the map cannot. Don't mean to put you on the spot. But the difference is that the set can have duplicate keys.
That's right.
Yeah.
It's
So
a tuple.
exactly, right? It's just a list of tuples. So the map enforces that there's only one value per key, but the set doesn't. So we had to write this, and we had to handle the notion of failure, like when there's duplicate keys. And so we wrote a function to do that. But the function's really big, and I'm not going to like talk about all of it. The reason it's really big is because there's some error handling stuff in it. But the bulk of it is actually pretty small. So I'm actually just going to focus on this little function here at the top. And in fact, I'm not even going to focus on this function, even though this is pretty small. I'm going to focus on even just like a helper function in that function. So this is all I'm going to focus on. This is the tiny piece of code that I'm going to talk about basically for the remainder of this talk. And this is a function called grouped. And this is just a small piece of the implementation of that function. And if I added a type signature on it, so you probably can't read Haskell type signatures, but that's okay. I'll read it for you. It basically says, given a list of tuples from keys to values, produce a list of lists of tuples from keys to values. And what this does is it takes all the tuples with the same key and it like bins them up. It puts them in the same group, right? So if you have duplicate keys, they'll end up in the same sublist. Now, that's not very difficult to describe, but if you actually said, all right, like how would you go about implementing such a function, it might be a little bit more complicated than you might think. In Haskell, though, it's a really simple one-liner, and I'll read it to you because you probably don't know Haskell syntax. But this is basically saying the grouped function is equal to group by equality on first. That FST is the first operator, and it's a function that gets the left-hand side of a tuple, the first element in a tuple. So what that means is basically we're saying call group by, and we're going to group by equality because we want to group on the equality of the keys on the first element of each tuple. Does that make sense?
Yeah.
All right. So that's really cool, and it almost kind of reads like English, but like how does this work, right? This is a really dense function, but it's not that hard to read. And what's really cool about it is that if you look at it, like there's no variables in this function. We didn't specify like, loop over each tuple and do something on it. Every single aspect of this function is built out of actually 4 just built-in library functions. And they're equality, the first operator, the on operator, and the group by operator, which are all just built-in functions. And I put their types here, and I'm going to kind of walk you through like how these things fit together. And even if you don't understand all the details, that's okay. The types are obviously not required. You can do all this stuff in a dynamically typed language, but I like the types here because they illustrate how a lot of the time the types in Haskell help you figure out how to like put little pieces together, right? They're like helps you figure out how to like fit these jigsaw pieces together to build something bigger. They're kind of an algebra of composition. So the equality function, the one at the top here, is really simple. Given like an A and another A, you get a bool. So if they're the same, you get true. If they're not the same, you get false. The first function, also really simple. You give a tuple of A and B, you get an A. It's not very complicated. But the second 2 functions are a little bit more complex. So I'm going to talk about group by first. Group by takes a function and a list. And the function basically says, are these 2 things the same? Right? So the function basically takes 2 A's and it produces true or false. So if it's true, then they're the same. If it's false, then they're not the same. And then it takes a list and it produces a list of lists. So it bins them up. It puts them into groups. But here's the trouble. Like, we want to group by equality. But we don't want to just compare all the tuples to see if they're equal to each other because we only want to focus on the keys. And so what we want to be able to do is kind of reuse this group by this equality function, this first function. But how do we do it? Well, what we would have to be able to do is apply first to each tuple that we're comparing, right? Get the keys out, and then feed those to the equality function so that we can test if they're the same. But it turns out that Haskell comes with a function to do that built in. It's called on. And so it looks kind of scary, but it's not as bad as it looks. It basically takes 2 functions and it produces a function as a result. So the first function is like a comparison function, the B to B to C part. So it basically says, like, given two B's, if you produce a C, then the result of the whole function will be C. And then you take kind of like a function that maps like a big data structure to a smaller piece of that data structure, which is the A to B part. So you can think of it like the A is the tuple, and the B is the key. And then you take the two B's, which are the two keys, and you feed them to the equality operator to see if they're the same. And then you get a result. And so the result is A to C, which does that whole operation. So by doing that, you get this really, really concise way to just build a complicated function out of really small pieces. And it's not even that hard to read. It's like a nice, readable way to do it. Now, this might seem contrived. This might seem silly. It might seem like I'm harping on this one really tiny example for no reason. But I wrote this same function in another programming language. I wrote it in Java. And it looks like this. It's about 15 lines of code, whereas in Haskell it's 1. Now, I feel like this might come off as bagging on Java. That's not my point here. You could write the Haskell version in Java, but like those functions that group by on, those aren't available in the Java standard library. So if you wanted to implement it yourself, this is really the best I could do. Like I'm not making Java look worse for the sake of demonstration. Like this was the best I could do, and if you can come up with a better implementation of it in Java that's shorter, I would love to know about it. But the point is, like this basically goes from 1 line to 15 lines. I think this is a lot harder to read, and it might seem silly, but that adds up, right? When you've got a function that's 20 lines long, 20 times 15 is 300 lines of code. It gets a lot bigger, really, really fast. And so one of the really big advantages, I think, of functional programming, which object-oriented programming really doesn't get you, is this notion of code reuse. Because I think one of the big promises of object-oriented programming has always been code reuse. But it never really seems to work out in practice. You always end up having to define your own little classes to do the same things over and over again. But functional programming, that like separation of data from the logic really, really, really helps. So, again, just kind of to recap, if you're interested in writing functional programming, if this convinced you that functional programming is a worthwhile thing, or if you already thought that functional programming was a worthwhile thing, focus on, writing functions, composing functions, keeping them small. Focus on separation of logic and data. Don't focus so much on the details. Like monads are not an important concept to writing just standard functional programming. Lenses, they're a useful functional programming tool. They are not what makes functional programming. Basically just really focus on how you're structuring your program first. The details kind of fall into place second. And if you do structure your program this way, you might run into problems where you say, oh, I've got this issue. You might find out, oh, it turns out that lenses were designed to solve that problem. And then it'll make sense. Approach it that way, rather than trying to learn all these fancy buzzwords and then trying to shove them into your program, because that won't really be helpful. So that's really it. That's all I've got. Any questions?
So you're showing that this Java program has 15, 20 lines of code.
Yeah.
In the other one, the functional programming one, right?
Yeah, this one.
This one. But group by is on, and the FST have its own implementation to kind of hide it in the background, right? But if you add them up together, the number of lines might be similar.
Yeah. That's a good point. It's certainly true. Like the complexity does not completely go away. It's just that you don't have to write it yourself, right? Those functions are in the library somewhere. Similarly with Java, you could say I have a list of tuples and I have an array list, and if you inlined all that into this function, it would be enormous, right?
Right.
So yeah, it's not so much that it is a much easier way to approach the problem, as you say. It's just that you can reuse a lot more.
That's right. Yeah.
Yeah.
I agree.
So you don't have to reinvent the wheel constantly. And that's just one aspect of the reason I think functional programming is nice. But definitely data transformations are one of those areas where the functional style that is really, really clear and easy to understand. Whereas I think the imperative style of focus on every little thing adds a lot more cognitive overhead.
I agree. And this one, it's mutating, right? Because you do
Right.
stop, put,
Right.
add.
Yeah.
This is a very small example. Let's say it's bigger.
Yeah.
Who knows what other places that touch bins?
Yeah. Yeah.
Functional
Yeah.
programming kind of takes away that
Yeah,
risk.
yeah. And it's a good point too. Like, a lot of the time, I think people get hung up on the idea that, oh, if everything I write is pure, how do I get anything done? What if I need to mutate something? And like, what's the advantage of just like, if I'm gonna write a functional programming, I could just write pure functions and just not mutate things when I don't want to mutate them. You can do that even in an imperative programming language. But the advantage, I think, of keeping things, like of having a strict rule, keeping things pure, is like you say, you can predict, you can say like, I know that's not going to change. I know, and so it makes it easy when you're reading a program to be like, I have strong guarantees, and I know that these things are going to hold true just from reading the program. So yeah, it decreases the cognitive complexity a lot for certain kinds of programs. And the amount of code, like we were recently rewriting some Java code just kind of as a prototype. A little bit unfair because this is just a prototype rewrite. We doesn't do all the things that the original did, but we were able to implement like something that takes thousands, if not tens of thousands, of Java code, and get like 85% of the way there with 150 lines of Haskell. And again, that's not fair because it's like the last 25 or 15% that's the most complicated, all the edge cases and corner cases. But it really does reduce, and shorter code, like yes, it can be harder to understand if it's like made too concise. But a lot of the time, for the most part, as long as you're not like gulfing your code, shorter code is easier to read. There's less code to read. There's less code to understand. So, there's an advantage to conciseness. All right, that's it.
That's my question. Thank you.
Thank you.